Yeah, like whenever I told him he was like shocked.
Yeah, mine was wrong.
Jillian people. What's that? About the boss.
Yeah.
Yeah.
Yeah, the same.
Yeah. Oh, that was really interesting.
Yeah.
Oh, yeah.
Hi everyone, welcome to our seminar. I'm going to introduce Dr. George Starmer. George Starmer is a data scientist, educator, and musician. He is the founder and CEO of StatQuest, an online educational platform that teaches data science, machine learning, and statistics. He is also the lead AI educator at Lightning AI and a member of the board of directors for the Society for Scientific Advancement. Prior to this, he was an assistant professor at the University of North Carolina at Chapel Hill, where he developed statistics and visualization methods for high throughput sequencing technologies. Please give him a round of applause.
This is my quest to StatQuest, and it's gonna be clearly explained. Hooray! Hey, can the people online, can they hear? How do we know that they're hearing things?
Yes,
Affirmative, hooray, okay. Note, this seminar will probably be a little different from what you're used to. The big difference is that I'm going to read everything right off the slide like I'm doing right now. I do this for two reasons. One, often for people that speak English as a second language, reading can be easier than listening. So if you're familiar with a sing-along, think of this as a read-along. And also, generally speaking, when I script every single word, the stuff that comes out of my mouth makes more sense. In other words, I'm just not good at telling a story without writing it down. Also, and I don't actually know if this is true, it may be purely anecdotal, but I've read a few places online, which is very reputable because it's just online, that if you read and you hear the exact same things at the same time, it helps with retention. I don't know if that's actually true. It's just something I saw on the internet and I believe it. Not really. I want to see some data. I mean, I'd like to believe it. Okay, so with that said, let's get started. Hooray. If you don't already know, my name is Josh Starmer and I run a YouTube channel called StatQuest. I'll tell you more about this picture later. Every day, people around the world watch StatQuest to learn statistics, beep, boop, 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 machine learning, beep, boop, 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 and other data science subjects. Beep, boop, beep, beep. Okay, more importantly, people say StatQuest helped them win data science competitions, pass exams, graduate, and get jobs and promotions. Hooray. So far, no one has told me that StatQuest helped them get married, but maybe one day it'll happen. That'd be cool, right? You know, who knows? People watch StatQuest because it makes complicated sounding things easy to understand. And here's some nice comments that people said about me in my channel. And he said, awesome. Anyway, believe it or not, creating a YouTube channel was never the plan. Instead, when I was in high school, I wanted to become a classical cello player. And that's a picture of me in high school with my string quartet. I got the cello, obviously. That's me again, back in the day. I used to dream about playing the Elgar Cello Concerto like Jacqueline Dupre. If you're not familiar with the Elgar Cello Concerto, I'd highly recommend checking it out. It's awesome. And she played it great. Anyways, I ended up going to Oberlin, which is a school up in Ohio. It's a tiny school, but they have a music conservatory. So I got a degree in music from them. So I got a bachelor's in music composition. And just to be safe, My parents made me. I got a Bachelor of Arts in Computer Science. So I ended up with two possible career paths. And this is one of those things where I hate to say that my parents were right, but they were. It's embarrassing. Because when I was 19 years old, I was so certain. I had it all figured out. Okay, anyways, on the one hand, I could potentially become a professional orchestral musician. Or I could become a professional coder. On the surface, being a musician seemed glamorous. You get to wear fancy clothes. Look at me now. You spend time with fancy people. And but it's fundamentally boring, at least to me. And here is why. Beethoven wrote his Fifth Symphony in 1808, over 200 years ago, and it has not changed much since. Don't get me wrong, Beethoven's Fifth Symphony is awesome, but playing it every year for the rest of my life might get tedious. In contrast, being a coder seemed like the exact opposite of glamorous. You get to wear, these aren't jeans, but you get the idea, and t-shirts. Fancy people tended to avoid coders. We were nerds. Fundamentally exciting though. What? Coding? What are you talking about? At least to me, I thought coding was fundamentally exciting. Why? Because languages, frameworks, problems, everything's always changing. There's always something new to learn, and I love learning. Okay, now despite the fact that I actually like to dress up from time to time, and I think it's really cool that I once talked to Yo-Yo Ma, who's a super famous cello player, and I talked to him in person. And thus the superficial things about being an orchestral musician had some appeal. I ended up focusing on the more fundamental differences between being an orchestral musician and a coder. And by the way, you can also replace orchestral with rock and roll. I was in a touring rock band, used to play the 40 watt back in the day. I've done the whole rock thing as well, okay? And this applies. Beethoven's Fifth, obviously great, but if you're in a rock band and you have a hit song, you have to play that hit song for the rest of your life until you die. It gets boring. I mean, I know it's not supposed to because it looks romantic and awesome, but after like 500 nights, every night for the rest of your life, you're like, ah. Anyways, it applies. Okay, so I focused on the fundamental difference between being an orchestral / rock and roll musician and a coder. Now, I had a few opportunities to talk with professional orchestral musicians, and they were a pretty sad group. And this is the same with the rock people. They were all burned out, and they'd lost their passion for music. Just as I expected, playing Beethoven's Fifth Symphony every year for your whole life gets boring. So this thing about music being fundamentally boring was something I'd seen and experienced firsthand in real life. So I've ultimately picked coding over being a musician because I wanted a job that would always be exciting, at least to me. Bam? Not yet. Although I came to the conclusion that being a coder was fundamentally exciting, it was also fundamentally scary. And it's scary for the exact same reasons that it seemed exciting. In computing, everything changes all the time. What that means is that a lot of the skills that I learned in college would be obsolete in a few years. People no longer program in Perl. I'm a great Perl programmer. That skill is not very useful anymore. And at the same time, my skills became obsolete. New people would graduate and enter the job market having mastered the latest, greatest new skills. So at the same time, I was like, I know Perl. They're all like, well, I know Python. And I'm like, I got to learn Python. So I imagine the life of a coder as being a life of always playing catch up. Python's awesome. It'll go away. You know, when I was a kid, everyone was doing things in C. You know, C's still around, but it's not hot like it was back in the 80s. And And Python is hot now. It won't be hot. I mean, ChatGPT is going to code for us in a couple of weeks, right? We're not going to have to do it anymore. Things are going to change. You just have to know it. And whatever you're doing right now, if it's in tech, you won't be doing it in 5 to 10 years. You'll be doing something different, okay? So I imagine I'd always be playing catch up with younger people that had just learned the latest skills. And that's when I decided I needed to learn statistics. Just like Beethoven's Fifth Symphony, the t-test that we use in statistics has not changed much in a long time. So in some sense, t-tests will get boring sooner or later. But with big data, I can combine t-tests with computing to keep things interesting. So with statistics, I thought I would get the best of both worlds. Something that doesn't change every 3 years combines with something that does. And that's bioinformatics, right? You guys are in bioinformatics. So you're in the sweet spot. Bam. Okay, anyways, I used to work in a lab helping these guys with their statistics. And although I was doing all the math, I wanted them to understand what I was doing so that I could speak, so that they could speak confidently and correctly about their results at conferences. So I started to give little presentations on statistics for the lab every Friday morning. But this was an academic lab, and new people were coming and going all the time. So I thought it might be better to put the presentations on YouTube. Boom. Putting the presentations on YouTube solved 2 problems. 1, it spared me from having to give the same lecture every 3 to 6 months. So it's a time saver for me. And 2, maybe even better and more important, it allowed people to get the information when they needed it rather than when I had time to teach it. So I could teach R squared, but they may not need to know R squared for another 6 months or a year, or who knows when they're going to need to know it. But when it's on YouTube, it's there when they need it. And they don't have to call me up in the middle of the night and go, hey, Starmer, what's R squared again? I can't remember. You talked to me like a year ago. Just watch the video. Go back to bed. Okay. So now let's talk about some of the things that have helped my YouTube channel be successful. So I've got these rules. Rule number 1 is focus on the main ideas. So imagine we wanted to teach someone how to drive a car. Should we start by teaching them about fuel injection? Or should we start by describing the master cylinder? And what about the head gasket? Even though fuel injection, master cylinders, and head gaskets are critical parts of cars, they are not the main idea. In other words, we don't need to know about these parts in order to drive. In fact, even though I bet most of the people in this seminar know how to drive, I'd be surprised if you knew about these parts. If I wanted to teach someone how to drive, I would focus on the main ideas. I would start by teaching them about the brake pedal so that they can stop the car. Stopping the car is the most important thing to teach first so that we can avoid hurting other people. Then I would teach about the steering wheel so that they can turn the car. The steering wheel is the second most important thing because we can use it to avoid hurting people. Again, we don't want to, have a tragedy while we're learning how to drive. Lastly, I would teach them about the gas pedal so that we can finally move the car. The brake and gas pedals and the steering wheel are the main ideas of driving because you need all 3 to drive, but you don't need anything else. Knowing about the brake and gas pedals and the steering wheel may not make someone a great driver or a very knowledgeable driver, but at least they know enough to practice and they can easily learn more. Bam. Similarly, when I want to teach someone about a neural network, I would not start with some complicated looking equation. Even though understanding this equation takes a lot of work and makes me all proud of myself, it's not the main idea of neural networks, and it never will be. Instead, all this is a compact notation for describing what's going on. That's all it is. It's very different from the main idea. It's important to never confuse a compact notation for the actual main ideas. So instead of a complicated equation, I would start out with a super simple data set that showed whether or not different drug dosages were effective against a virus. The low and high dosages were not effective, but the medium dosages were. Then I would show that fitting a straight line to that data isn't very helpful. Because no matter how we rotate this line, it can only be close to 2 of the 3 clusters of points. So what we really need is to fit a squiggle to the data. And the main idea behind neural networks is that no matter how fancy they look or sound, all they do is fit squiggles to data. Now that we understand the main idea behind neural networks, we can dive into the details. Like these nonlinear functions are called activation functions. And because the activation functions are between the input and the output, we can say that the activation functions are in a hidden layer. And there's lots of other details, but we'll save them for later because right now we're focusing on the main idea. And the main idea of neural networks is that they fit squiggles to your data. So this is rule number 1, and it's the most important rule of all. It seems simple, but it's easy to be distracted by things that are not the main idea. For example, when we were talking about cars, we were talking about like the master cylinder and fuel injection and things like that. If you watch a car commercial, you're watching TV, they're not telling you like our car has a brake pedal and a steering wheel and a gas pedal. No, they're talking about we've got this kind of fancy fuel injection. They're talking about all these things that are not the main idea. So it's easy to get distracted and think, oh, there's other things that are really important because I was watching TV and all they talked about was how important fuel injection was. And that's not the main idea. So it's hard to focus on the main idea, especially when there's a lot of hype like there is around neural networks, and there's tons of hype on neural networks. Okay. So rule number 2 is know and have empathy for your audience. Everyone has different experiences, backgrounds, and perspectives. And it is important to keep this in mind when explaining anything. For example, if I'm going to teach someone how to drive and they know how to ride a bike, then I'll explain how to drive in terms of how to ride a bike. And the handlebar is the steering wheel. And the pedals are the gas, etc. In contrast, if they knew how to ride a horse, then I'd explain how to drive in terms of how to ride a horse, which would be very hard because I don't know how to ride a horse, but I would try hard because I've seen it in movies. And I'd say, it's kind of like getting on a horse, I guess. Okay, so giddy up. And if someone had piloted a boat before, then I would explain how to drive in terms of how to pilot a boat. And I do have a funny boat story, and I'll save that for bowling, okay? So come bowling later. Okay, anchors away. Okay, when I make my videos, I specifically think of my old coworkers in Terry Magnuson's lab at UNC. By making videos that communicated statistics to a bunch of geneticists, I ended up with videos that communicated statistics to people all over the world. And this is another thing. You guys are bioinformatics people, right? Yes. Okay. So that means you have to talk to biologists. You have to talk to statistics people. You've got to talk to all these different people who have different backgrounds and different frameworks. And you have to be like chameleons in a way, or translators. Because when you're talking to the statistics person, you got to talk to them one way. And when you talk to the biologist, you got to talk to them in another way. So you always have to kind of know who you're talking to. And if you mix them up and you talk to the biologist the way you talk to a statistician, they'll punch you in the face. You don't want that to happen, right? So it's good to know who you're talking to. And so I specifically think of my old coworkers at UNC. And in fact, a week from today, I'm actually presenting for this old group of coworkers, my latest video, to see if I can still convince them or teach them how things work. And the goal is for them not to fall asleep while I'm talking. And there's this one guy, he's not in that picture, his name's Dom, and he is a tough one. So I've got my work cut out for me. Okay, so lastly, when you don't know your audience, try your best to explain in a way that anyone could relate to, and that's tough. And try to anticipate questions from people that have different backgrounds and experiences, and that's hard to do too. But one way to explain things so that anyone can relate to the subject and helps anticipate questions is to use pictures. So that leads us to rule number 3, which is use pictures. A lot of people are visual learners. If you're not a visual learner, and it's easier to look at this equation than it is to look at this graph, then you need to make sure you understand rule number 2, have empathy for your audience, because that's another punch in the nose you got to be watching out for. These people are tough. Okay, regardless of whether or not you're a visual learner, visual cues often make things easier to remember. Okay, here's an example of some unvisual directions to the grocery store. Go straight ahead 731 meters. Turn pi divided by 2 radians. Go straight for 1,196 meters. Turn 3 pi divided by 2 radians. And then go straight for 52 meters. Bam. Okay, you guys ready? There's a pop quiz. No one thought there was going to be a quiz. Okay, can anyone remember the first step in the directions to the grocery store?
31 meters.
Are you kidding me? 7, who said that? We have a winner. Okay. Did anyone else know that? Okay, so, and why, right? Yeah. Okay, this may be precise and accurate, but for some people, and I'm not going to name names, but I consider myself a member of this group. It's hard to remember. Here's an example of visual directions to the grocery store. Go straight till you get to the gas station. Turn left. Go straight till you get to the playground. Turn right. Go straight till you get to the grocery store. Bam. Okay, to summarize this rule, we almost always have a choice between not using pictures to explain something and using pictures to explain something. Pictures are, 1, easy to relate to, often help people answer their own questions. For example, we may not have anticipated that they don't actually know what grocery store we're just saying, these are directions to the grocery store. And they're like, what kind of grocery store is it? Well, it's a Whole Foods. You can tell just by looking at the picture. Or you could say, go straight to the gas station. They're like, what gas station is it? It looks like it's a BP station. So without even having to do anything, we're anticipating questions and we're answering them without having to do any extra work. That's a bam. Okay, and relatively easy to remember for people like me. Not everybody. Okay, bam. Okay, rules 4 and 5, repetition is helpful and do the math. This step is going to take a long time to get through because we're going to do lots of repetition and we're going to do lots of math. So brace yourselves. It's just going to be hard. Okay, so no matter how simple the equation, plugging in a few numbers makes it way easier to understand and explain. And doing this more than once makes it way easier to remember. However, complicated looking things Plugging in the numbers is crucial and can provide deeper and more memorable insights. For example, let's plug some data into this neural network. However, first, let's remember the main idea. Neural networks fit squiggles to your data. So the goal is to figure out how this fits a squiggle to the data. Okay, so with that said, to keep the math simple, let's assume dosages go from 0 for low to 1 for high. Okay, the first thing we do is plug the lowest dosage, 0, into the neural network. Now, to get from the input node to the top node in the hidden layer, this connection multiplies the dosage by negative 34.4 and then adds 2.14. And the result is an x-axis coordinate for the activation function. Note, these values come from fitting the neural network to data with a method called backpropagation. And that method is beyond the scope of this seminar. We'd have to sit here for another hour, and we don't want to do that because we haven't had lunch yet. But if you're interested, there's a video on it. You can check out the quest. But for now, you guys, are you familiar with linear regression, right? And you have like these slope and intercept, and you have to find the optimal values for those. And you do that by fitting, you could do it iteratively, or you can do it directly with the derivative. So imagine these values in these boxes are like these. These are the things that we solve for when we fit that line to the data. We got our y-axis intercept and we got our slope. And it's interesting that we also, we've got a number we multiply the input and we've got a number we add. And here we're multiplying the input and we're adding. Okay, so we're actually doing the same thing that this equation does, just with different numbers, right? And earlier, behind the scenes, before you guys were watching, I fit this to our data. It's because, and the reason why we have backpropagation, I'm just going to skip to this. The reason why we have backpropagation is because there's a closed form solution for just linear regression, and you can solve for directly. Unfortunately, for neural networks, there's no closed form solution. So we've got to do something that is iterative and approximates an optimal solution. So, okay, we're good that these are just values that we've just imagined we're solving. We're just plugging into numbers like this, and we're calculating y-axis coordinates, right? No big deal. Bam. Yes. Okay. Okay. Now, given that we have already estimated these parameters, the lowest dosage 0 is multiplied by negative 34.4. And then we add 2.14. And to get 2.14 as the x-axis coordinate for the activation function. To get the corresponding y-axis value, we plug 2.14 into the activation function, which in this case is the soft plus function. Note, if we had chosen the sigmoid curve for the activation function, then we would just plug 2.14 into the equation for the sigmoid curve. It's no big deal. But since we're using the soft plus for the activation function, we plug 2.14 into the soft plus equation. And the log of 1 plus e raised to 2.14 is 2.25. And just to be clear, in statistics, machine learning, and most programming languages, the log function implies the natural log, or the log base e. So if you're doing this math at home, that's why we got 2.25. Anyway, the y-axis coordinate for the activation function is 2.25, and it's right there, boom, right on the curve, right? Okay, so let's extend this y-axis up a little bit and put a blue dot at 2.25 for when the dosage equals 0. Now, if we increase the dosage a little bit and plug in 0.1 into the input, the x-axis coordinate for the activation function is negative 1.3. And the corresponding y-axis coordinate is 0.24. So let's put a blue dot at 0.24 for when dosage equals 0.1. And if we continue to increase the dosage values all the way to 1, the maximum dosage, we get this blue curve. Bam. Note, before we move on, I want to point out that the full range of dosage values from 0 to 1 corresponds to this relatively narrow range of values from the activation function. In other words, when we plug dosage values from 0 to 1 into the neural network and then multiply them by negative 34.4 and add 2.14, then we only get x-axis coordinates that are within the red box. Does that make sense? That any number between 0 and 1 is only going to give us a number in this range. It's not going to give us a number way out here, just in this little window. And thus, only the corresponding y-axis values, only these things up here in the red box are used to make this new curve. And we take this, basically we're taking this and we're flipping it because we've got a negative sign. We flip it and bam. Okay, cool. And now we scale the y-axis values on the blue curve by negative 1.3. For example, when dosage equals 0, the current y-axis coordinate for the blue curve is 2.25. So that's that point on the curve, and that's that blue point over there. And now we're going to multiply it by that. So we multiply 2.25 by negative 1.3, and we get negative 2.93. And negative 2.93 corresponds to this position way down on the y-axis. Likewise, we multiply all the other y-axis coordinates on the blue curve by negative 1.3. And we end up with this new blue curve. Bam. Okay, now let's focus on the connection from the input node to the bottom node in the hidden layer. However, this time we multiply the dosage by negative 2.52 instead of negative 34.4. And we add 1.29, excuse me, instead of 2.14 to get the x-axis coordinate for the activation function. Now, if we plug in the lowest dosage, 0, into the neural network, the x-axis coordinate for the activation function is 1.29, right there. And now we plug 1.29 into the activation function to get the corresponding y-axis value. And we get 1.53 right there. And that corresponds to this yellow dot. So that's 1.53 up on the y-axis. Now we just plug in dosage values from 0 to 1 to get the corresponding y-axis values. And we get this orange curve. Note, just like before, I want to point out that the full range of dosage values from 0 to 1, in this case, it only corresponds to this narrow range of values, right? When we plug in values from 0 to 1 here, we only get x-axis coordinates in this little sliver, and we don't get values out here and out here. So we're actually cutting a smaller slice of the activation function than we did before. I might have gotten ahead of myself. So in other words, when we plug in dosage values from 0 to 1 in the neural network, we only get x-axis coordinates that are within the red box. And thus, only the corresponding y-axis values in the red box are used to make this new orange curve. So we see that fitting a neural network to data gives us different parameter estimates on the connections. And that results in each node in the hidden layer using different portions of the activation functions to create these new and exciting shapes. Do you guys have that? Okay, double math then. Okay, now just like before, we scale the y-axis coordinates on the orange curve. Only this time, we scale by a positive number, 2.28. And that gives us this new orange curve. Now the neural network tells us to add the y-axis coordinates from the blue curve to the orange curve. For example, when dosage equals 0, the y-axis coordinate on the blue curve is negative 2.93. And the y-axis coordinate on the orange curve is 3.49. And when we add negative 2.93 to 3.49, we get 0.56, that green dot. Likewise, we just keep adding the y-axis coordinates from the blue curve to the orange curve. And that gives us this green squiggle. Then, finally, we subtract 0.58 from the y-axis values on the green squiggle. Boop. And we have this green squiggle that fits the data. Triple bam. To summarize, we started out with two identical activation functions. But then we plugged in some values, and we saw how using multiplication and addition slices, flips, and stretches the activation functions into new and exciting shapes, which are then added together to get a squiggle that is entirely new. Bam. And the squiggle is then shifted to fit the data. Now remember, the rules we just illustrated here. Repetition is helpful, and do the math. By plugging numbers into the neural network and doing the math, we have a better understanding of how this neural network fits the squiggle to the data. Doing the math usually requires using relatively simple examples. In this case, I created the simplest neural network that could illustrate the main idea, that we're fitting a squiggle to data instead of a straight line. For me, one of the hardest parts of my job is coming up with relatively simple examples. If you look on the internet for like neural network examples, everyone uses this character recognition example, like how to translate numbers into like predict like, oh, that's a number 3 or something, like character recognition, which is cool. And neural networks can do that, and that's amazing, right? But the neural network required to do that is so complicated that you can't visualize what the shape of the data is and how it's fitting a squiggle to that data, right? Because ultimately we've just got pixels, and intensities, and it ends up just being a big blob of data, of points, basically, in a high dimensional space that's too high dimensional for us to actually look at. And so we can't, even if we wanted to, we can't draw that picture. So I had to come up with like a much simpler thing, because I wanted to see it, because it wasn't enough just to believe that it worked. I had to see it work, and I had to understand why. And by doing that, I was able to see this insight that we're taking just little chunks of this thing, these activation functions, and we're twisting them, and we're flipping them, and we're stretching them. And then we add these different shapes together. And it's that adding of two weird looking shapes that gives us this squiggle. And it's also interesting, I don't know if you notice that, it doesn't really fit, it fits the data perfectly. But outside, in between the data, it doesn't fit it perfectly. That's an interesting insight we would not have gotten if we couldn't see how this is working. So this is an interesting thing. Neural networks can fit the points perfectly, and it does, but in between, the neural network can do what it wants. And we wouldn't have known that. We wouldn't have been able to see it if we couldn't draw it. And so that was a big insight for me when I was teaching myself neural networks. I was like, oh, so that means in between the data that the neural networks is seeing, the output could be unpredictable, because it does not extrapolate the way you and me would do it. The way you and I would do this, we would fit a nice bell-shaped curve to this data, like a normal curve or something, and it'd be nice and awesome. But the neural network doesn't care about normal curves. Neural network says, these are the data you gave me, and I'm going to fit them, and that's all I'm going to worry about. And everything in between, who cares? And so I think about that when people talk about getting neural networks to drive cars. Anyways, once I have a relatively simple example, everything else becomes relatively easy. Okay, rule number 6 is always start with data. And you may remember that when we started to talk about neural networks, We started out with this super simple data set and showed that a straight line would not fit the data well. So we needed to fit a squiggle to the data. Knowing that we need to fit a squiggle to the data gives us a context from which we can understand neural networks, right? Why are we learning this thing? What's the big deal? Who cares? Well, we're like, well, we've got problems. We got data shapes of that data can make that we may not have a good function that can fit. And especially if that function or that data is really high dimensional and we can't see it, we can't say, oh, that we could just fit a normal curve to that. We have to come up with something that can automatically fit a shape to data. And that's what neural networks do. They look at data and they go, I don't care if we can look at it or not. I'm going to fit a shape to you. Bam. Okay, in other words, we know that the goal of this fancy looking thing is to fit a squiggle to the data. And in general, knowing what the problem is and why other methods fail to solve it, help us understand why we're doing all this math. Okay, rule number 7, limit the presentation of 3 main ideas, which seems contradictory, but I didn't say these were main ideas. I said these were rules. There's a difference. Anyways, for neural networks, main idea number 1 is that we start with identical nonlinear activation functions. Nonlinear is key. I didn't harp on that, but if they were just linear, if this was just a straight line, then we'd add them together and we just get another straight line. It's the fact that there's a curve or a bend or something weird going on that allows us to create more complicated shapes. Bam. Main idea number 2 is the activation functions are sliced, flipped, and stretched into new and exciting shapes. And we say double bam. And then main idea number 3 is that the curves are added together in the end. So we have the little pieces of curve and we add them together to make a squiggle that is entirely new. Bam. Triple bam. Note, if you came to this seminar not understanding how neural networks work, there's a good chance that you now know. And you came to that understanding by looking at pictures and doing some basic math, just multiplication and addition with a little like log and exponential here, but we're not going to talk about that. Okay, and we completely ignored this equation. Again, this is because the equation is not the main idea. All it is a compact notation. I mentioned this because I did a little Twitter poll a few weeks ago. Well, I guess a few months ago. Okay, in order to understand neural networks, you need to first understand linear algebra. Of the almost 4,000 people that responded, 74% agreed that you needed to understand linear algebra before you can understand neural networks. In other words, 74% of people think you need to understand this equation before it's possible to understand this diagram of a neural network and how it makes predictions. However, in my opinion, it is the exact opposite. Instead, we need to start with this diagram and learn how it makes predictions first, before we learn about this equation. In summary, I believe that StatQuest, my YouTube channel, is successful because rule number 1, I try as hard as I can to focus on the main ideas. I don't always succeed, but I try. Rule number 2, I have empathy for the audience. Again, I do not always succeed, but I try. And my secret to that is I specifically have a handful of people that are my audience. You know, it's my former lab mates. I try to talk to them. 3, I use pictures. Those are helpful for some, not all. Rules number 4 and 5, repetition is helpful and do the math. And rule number 6, always start with data. And rule number 7, limit the presentation of 3 main ideas. I've noticed that if I try to do more than 3 BAMs in a presentation, it's better just to split it into 2 presentations. Too much, you know, it's like, I don't know, you go to, for me, I remember when I used to have to go to seminars and it was like I don't know how, like an octave BAM presentation. And I get to like the 3rd or 4th BAM and I'd be like, they weren't saying the band, but you know, they were how these things that you could tell they just had so much they wanted to convey. But I got saturated and I got frustrated because once I get saturated with information, I can't take more on. I can only learn, my brain can only learn so much in so much time. And it would just frustrate me when they were like, well, I'm just gonna keep going. And I'm like, what? I'm tired. So I say limit the presentation to 3 main ideas. And then I say the end, and I finished a little bit early so we can have questions or songs.
And we need to leave this room by 12:30 so we can have a short Q&A session. And if you are gonna meet George later, so I would suggest you save the questions for later. On the following event.
Okay.
Yeah, and I see Dr. Kanan.
Thanks for doing that. So I'm just wondering if you have any thoughts on how to address people with sort of some disabilities like hearing and visual impaired.
Yeah. So in theory, so I have, there's a couple issues that I come up against with color blindness. I try to use a lot of colors, as you saw, because to me, colors help differentiate things. But I'm very bad with my palette, my color palette, but there are tools you can use to check color blindness. I need to use those. I don't do it enough. And there's also blind people like, so there's people that listen to my videos. And I don't do this perfectly, but when I do the script, I often will be like, the script will be like, and the data point in the upper left-hand corner, I try to narrate everything so that blind people can, even though it's all in their head, I try to narrate all the details so that they can, just by hearing my voice, they can learn what's going on. I try to do that. And you just have to be very aware that you can't just say, there's data over there. You have to say there's a data and the way they're spread out means that we can't fit a straight line to them. And if we do try to fit a straight line, we can only fit it to 3, or they're in a triangle form. So you have to think about that. So yeah, if you're specifically trying to communicate to disabilities, you have to keep all that stuff in mind. And I try, I could do better. Yes.
Okay, my question is, so you're doing the StatQuest YouTube, you're explaining a lot of different things to people. How do you decide what topics you want to prioritize, and how do you like make sure you don't run out of things to explain?
Okay.
Yeah.
That was a problem I had early on.
Okay.
So early on, I was really just doing this for my coworkers, and it just was whatever they were doing. I already talked to Chris about this earlier. So one thing that was cool about doing this for my coworkers, it solved a couple of problems. They learned when they needed to learn, and I taught when I wanted to, basically. But it also meant that, like, my first video got 9 views in a year, and that was success, right? Because I didn't make a video for the whole world. I made it just for my coworkers, and I only had so many coworkers, and they were watching my videos, so it was a huge success. And so I just let them decide, because that was my audience. And in a way, they're still my audience, but things are a little different in that now people post comments. Can you teach transformers? Can you teach large language models? How does ChatGPT work? I get those questions 20 times a day. And so I started off like, once I, early on, once I got past t-tests and R-squared and linear regression, I was like, I don't know what I'm going to teach now. I was looking at like, and so I actually, if you watch my early videos, you're like, and if you have any ideas, post them in the comments below. I don't do that anymore. I got a to-do list that like goes and goes, because the thing is there's always new methods being created. And so there's always good stuff, but it's also sort of responding to the people around me. And it used to be that there were lab people with problems, and so I teach them what they needed to know. And now it's the whole world is like, hey, we don't understand large language models or how ChatGPT works. Can you teach us? And so that keeps me plenty busy. But yeah, just ask the people you want to teach.
I saw
There was an online question. And where'd it go? I'm gonna open the chat. Hold on, I gotta get the old man glasses. What does this say? What's the difference between modeling and machine learning? It seems like clinical physicians do not believe any data from modeling or machine learning. That's hilarious. They're modeling is just some. When I was a kid, I used to build models, like model planes, right? A model plane is not a real plane. It can't fly. I can't get on it. It's an approximation though. It's a much smaller approximation. It has the general shape. And for the purposes of me being an 8-year-old kid, it was good enough, right? It solved the problem of me not having anything to do in the afternoon on a rainy day. So that's a model, right? And what we end up with these days is we end up with, instead of like, I'm a person and I'm a complicated thing, and with a complicated brain, I guess. And so we can create a model of that. That's a simplification. It's not the same as my brain. It's a model of how the brain works. It's a handful of equations that when you plug in inputs that might be simulating oral input. And we can say, well, let's see what's Josh Starmer, how's he gonna respond to this sound? And we run it through the equations and we go, and we predict that I'll say, bam, when I hear that sound. That's a good prediction. There's a good chance I will say that. But so models are just basically anything that's simpler than the actual thing. And we use the simple things, the models, because the actual thing, maybe it's illegal or unethical to use the actual thing, or maybe it's too complicated to use the actual thing, or maybe we don't have the computing power to use the actual thing. So we use a simplification. Models, there can be different types of models. Some are statistical models, and those give us sort of, it's like doing a statistical analysis where we can have measures of variability, right? We can say, not only will Josh say bam, but we're 63% confident he'll say bam, and otherwise he'll say double bam, or something like that, right? We get measures of variation, and measures of variation are awesome, right? Because it gives us a sense of like what the range of applicability is and how much we can trust the models. And these clinicians apparently that don't trust the models, that may be something that they need to understand, is how to interpret the output of a more statistical analysis that gives us a sense of the variability. Because statistics is all about understanding and variation and using it to our advantage to make good decisions. But there's also, neural networks and machine learning type models, which are less statistical in nature and just tend to give you yes or no answers without a whole lot of bounds on the variation. And those models can be very helpful and very good, but they're also sometimes difficult to interpret in terms of like, what's the variation on that output? How much faith can I put in it? And there's ways around that. I was talking to Chris about this earlier too, in that we can test our model once we've trained it, once we've estimated all these values on this data set. We can throw new data at it that we know whether or not it was effective, and we can see how well this model works with that data, and that would give us some sense of like, it works good for data that's like right close to the actual training data, and it doesn't work so well for the in-between. That would give us some sense of understanding the range of applicability of that model. These are all very important things that we have to do. Maybe we don't do them all well enough or thoroughly enough, but it's stuff we can do. And so hopefully one day we'll teach the clinicians to have faith in science. Yeah.
Yeah, okay, I have another question. So this is kind of follow-up to my other question. So you're explaining things to a lot of people. A lot of people are watching these videos and getting good information from them, which is great. But how do you know that you're prepared enough to explain a new concept? And how do you make sure you've like taught yourself rigorously enough that you can explain to others and you feel confident that this is a good explanation that's going to help people?
Yeah. That's I could do a whole talk on that. But the gist is I read everything I can. And then what I do is I do the math by hand. And I also compare it to a real thing. Like when I made this neural network, I created like a real neural network in like using a neural network framework, and I trained it and I made it work, and I didn't know how it worked. So I pulled out these values and I just did the math by hand, and I made mistakes. And when I had the thing printing out intermediate values, and I had my intermediate math over here, and I could compare. And I drew this picture, and I made sure that ultimately everything matched from 0 to 1. I always got it. And then I took that program, and I basically just write a lot of programs that can validate that I've learned it correctly. I ended up writing this whole thing from scratch, and I ended up training it. I ended up writing my own back propagation algorithm to train it, and I ended up with the same values. And so I was just like, okay. And then I was like, well, let's generalize. Let's try something else. Let's try a different model, different input data, and see if I can figure it out. And I was able to figure it out. But it was kind of funny. In the end, it's kind of weird. I got so good at these things where I could just look at the data I was trying to fit, and I could imagine what these values would be. And I could just come up with them off the top of my head. And I'd be like, oh, that's probably this. And they would be pretty close to the optimized model. And I was like, I got this. But the other thing I do is I do drafts. I test them on people. A good way to understand that you don't understand is when you start teaching people and they ask you a question and they go, and what about this? And you're like, I don't know. That's a way. So for this video specifically, I tested it on like 10 different groups. There was like it was like COVID time. So it was like I was just zooming left and right. There was like a group in Turkey. They're like, teach us about neural networks. I said, I can't do that yet, but I can show you what I'm working on. And they were like, okay, we'll do that instead. And so we did that instead. And I said, any questions? And they would shoot me with tons of questions. And I'd be like, I can answer some of those. I can't answer all of them because I don't fully understand it yet. And I got to where I can answer everybody's questions. And I was like, I got this. So it's a lot of work, especially because I'm not an expert. I'm a student. I have to learn this stuff from scratch. I wasn't born knowing this. I never took a class on neural networks. I never took a class on machine learning. No one's ever taught this stuff to me. It's all been learned. But when I can make it work on my own I don't know, blah, blah, blah. We have to go. I'm sorry, but you get the idea, right?
Yeah.
I do lots of validation and lots of convincing, and I ask people questions. Okay, great.
Yeah.
Thank you.
For meeting. Because the blue rooms that probably.
Oh, that's every time I feel like throughout the seminar, I get colder and colder.
I think it's because it's always hot at the end of the day, and people like overcompensate.
Yeah.
And then it's cold, but.
I think I'm also generally more cold than hot. Actually, I think I have a 4. I think that's my theory.
So.
Because I'm always really hot or really cold.
Happy.
Yes. Never satisfied, just always. Hot, cold.
Yeah.
That song.